Hello friends, welcome to follow up. Let's have a look at today's daily challenge problem. Problem 1870, minimum speed to arrive on time. In this video, we are going to explain a solution based on binary search. Actually, this problem provides a typical use case for binary search in general. So here we are given a floating point number called hour and a list called dist. So the dist contains element describing the distance. So for each train, it can only depart at integer hour. So we may need to wait in between each train ride. So here is an example. For example, if the first train ride takes 1.5 hours, so we must wait for an additional 0.5 hours before we can depart on the second train ride at the hour 2 mark. So in this problem, we are required to find the minimum positive integer speed that all the trains must travel at for us to reach the office on time. Otherwise, we're going to return -1 if it's impossible. So here, the tests are generated such that the answer will not exceed 10 to the power 7, and the hour will have at most 2 digits after decimal points. So actually, this sentence gives us the search range, and you are going to see this point. So here are 3 examples. So in the first example, we see that if we travel at speed 1, so 1 plus 3 plus 2, which sums to 6, so it's on time, right? So also, if we divide by 1 using the integer, so the result will also be whole integer without remainder. So in the second example, so the output is 3. So the first train takes 1 hour. So 1 over 3 is 1.3, but not 1.3, 0.3. But we need to wait until 1. So similarly for the second one, it's an integer. So we just use 1 hour, 2 hours. So then 2 over 3 is 0.66. But in this one, we already arrived. So in the last ride, so we just count the actual hour. So it's 2.6 something, right? It's less than 2.7. So 3 is the minimum positive integer speed. So in the last one, so it's -1. So no matter how large the speed we choose, so actually, if you sum them together, so you need at least because the length is 3, so for the first 2 we need at least 2 hours, then plus some extra time, so it's larger than 1.9. So we return -1 for this case. Here are the constraints, like the length is bounded above by 10 to the power 5, and the distance is bounded above by 10 to the power 5, and it's an integer greater than or equal to 1. So hours is in this range. And there will be at most 2 digits after the decimal point in hour. So basically, if this is 10 to the power 5, and it has at most 2 digits, so if you multiply this by 100, then plus 1, this basically will tell us the search range. We are going to come into this point later. So here, actually, we are going to use binary search. So this is a very standard, I would say, strategy. So basically a binary search. So for this problem, we are going to do 2 things, or 2 steps. First is define a Boolean function, right, to produce order or monotonicity. Second is do binary search based on the Boolean function. So here are the 2 things: search range and the search range shrinkage. So we're going to specify all this. We're going to provide 2 versions. So one version is just a vanilla use of dict in Python, and the second one we're going to use NumPy to accelerate a little bit. So first, let's define the Boolean function. So basically, you can think of this. If we choose a very large speed, so it's more possible that we can arrive on time. If we choose a smaller time, we need to use more hours, so it's possible that we cannot arrive on time. So here, let's define can finish or can on time. So basically it accepts a speed v. So v is a positive integer, right? So here let's see how many what's the total time. So basically I'm going to use let's write without some finer details, right? So enumerate. So this. So for this, if I does not equals to this and this minus 1, in other words, not the last one. So we are going to let's do the division, right? Dev mode s divided by v, that is the time, right? If r does not equal to 0, right? So q is incremented by 1. In other words, we are computing the ceiling, right? So in this case, so anyway, so we are going to t increment by this q. Otherwise, so if it's last distance, so we're going to do this t increment by s over v, right? So overall, we want to check if t is less than or equal to the hour. So this is the Boolean function. So actually, in between, we can do some early check. If t is greater than an hour, we are going to return false. But for this problem, we're going to contain ourselves like this. And then this is the first step. And then the second step is to find a mean v such that can finish v is true, right? This is the problem logic. So for this, the search range, actually there's 2 points that we can have the search range. First is positive. Let's pick the lowest one, and then it says that so you can see here, right? Will not exceed this one, right? Hours will have at most 2 digits after decimal point, and also you notice that distance is at most 10 to the power 5. So here we can check 10 to the power 5 times 100, right? Let's plus 2 digits, right? Plus 1. So this is sufficient enough. So you can make it larger. So this not essential, but increase some extra time. So though it does not change the big O time complexity, right? So now let's do the standard binary search. So this is the if while low is less than high. So basically we're going to compute mid is low plus the shrinkage. So here we just shrink 1/2. So now let's check if can finish mid. So if this is the okay, right? So basically we can seek even smaller speed. So here we can set high is this one. So notice that high is making can finish true. Otherwise, so if it's not true, we need to increase the speed. So we are going to set low equals, because mid is mid yield false for this function. We're going to compute mid plus 1, right? So overall, what we want to return is high, actually. But here, let's make an X check. So if can finish, right? High. Otherwise, we're going to return -1, like in example 3. So before we improve the time complexity, the speed, not the time complexity. So we're going to first test that. Yeah, it passes the first example, right? And now let's look at the generic case. Yeah, it passes all the generic cases, but it takes a longer time. So here the time complexity is very easy to analyze. First, this function here is an ON function, right? And then we basically make O logarithm 2 high minus low, this number of search or call of this function, right? So basically it's 10 to the power 7, right? And then the overall time complexity will be something like this. So the overall time complexity will be, if we write like this format, it will be O logarithm 10 to the power 7 times O of n, where n is the length of this disk. But this one you can sort of write like this: 7, right, logarithm 10, right, times n. But this one in large is also a constant, right? But let's write it in this form. But if you like, so we write this like on. But we see that this constant matters in the overall speed, right? So this is the time complexity analysis. Now let's copy this function in the whole, and I want to improve the speed a little bit, not the time complexity. So here I'm going to mark this one as version v1. So here I'm going to use numpy. So import numpy CSMP, right? So I want to rewrite this part. So here, before we do anything, let's see, I'm going to comment this out. I'm going to transform this one to be an NP array, right? So this way we can use vectorization. So here, let me delete this part. And then first, we're going to do something like this. So dist over v. So v is an integer, and dist is a 1D array. So this actually involves broadcasting, right? In other words, each element in the dist will be divided by this v. And then we want to consider the ceiling, right? So t equals mpcell. So this one. So this will compute all the results in t to be its cell integer. But for the last one, we need to use the float number. So I'm going to reset the last one, which is going to be dist -1 divided by v. So this way, we just need to return, because this t is NP array, so it has a sum method. So we want to check if this is less than or equal to R, right? And then the binary search part basically the same, but this will greatly accelerate the running. So now let's do a test. So we have changed this one to be version v1. Now let's look at the second one. So let's first make a special case test. It passes the first one. Now let's look at the generic case. Yeah, it passes all the cases. Now it's much faster, right? So here actually the acceleration comes from this function. So here actually in this version, so we use vectorization for acceleration, right? So with that said, basically we provide a solution format to this problem. So actually you can write slightly variants of this binary search, but overall for general problem, typically we can first define Boolean function and to produce order or produce monotonicity. Then we do binary search. But in doing binary search, there are two things, actually three things that are very important. First is the search range. So search range should include all the possibilities. Secondly is how to do search range shrinkage. So this should be corresponding to the specific problem or use case. And the third one actually can be also important, that is the return. So what we want to return, what's the proper return. For example, in this problem, we are lazy, so we just call another time the function to see if this is the one we need to return. Otherwise, we return -1. So with that said, basically that's about it for this video. Thank you.